Andrew's not here today, so I will be introducing Reinhold, who needs no introduction. So we will just let him talk all about his new black hole formation results. So Reinhold, entertain us.
I'll try. Thank you, Cleo. Yeah, I think everyone knows me by now. I'm Reinhold Willcox, third year postdoc here at KUO. I'll be speaking today, as Eva introduced earlier, about the new LVK results that came out just a few months ago, and how our stellar evolution models actually have quite a bit of support from these new results. So to start, I'm going to go over what the new results actually showed us. So this is a plot that may be familiar to many of you. These are the masses in the stellar graveyard. These are all of the black holes and neutron stars observed in either gravitational waves or electromagnetically that we've seen to date. So the blue ones are the merging binary black holes. Yellow at the bottom are these are the neutron stars. The red ones are red are electromagnetic neutron stars. Getting all carried away. Black are electromagnetic neutron black holes. These yellow ones are electromagnetic neutron stars, and the orange ones are the gravitational wave neutron stars. The point of this is just to show where things are clumping up in the diagram. This diagram has, as far as the gravitational wave systems, nearly doubled because of this recent data release. So we now have approximately 200 observed detections. We had about 100 before. So we've doubled the number of blue things, roughly. Highlights of this data release include the highest SNR event to date. This is GW 230814, where the numbers are just a date, so 2023, August 14th. This had an SNR of 42.1, so we have this here on the bottom, compared to the first ever detected gravitational wave on the top, 150914, which was already incredibly bright and clear. You can see right, especially at the chirp there, the error on the signal is really quite low. Compare that to this most recent one, and you can really see kind of all the way through it. It's a really nice signal for testing things like GR at the extremes. But I'm not going to talk about that system so much. We also have a few interesting features here. We have the most massive detected binary to date. This is 231123. This is thought to be a 137 plus a 101 solar mass merger. There's a lot of questions around this one, a lot of cool proposed formation channels, but also you can see Mendel 2025 for arguments for why this may not be as high mass as they thought. Maybe it's a statistical outlier. Also some with a distinctly unequal mass ratio. You can see here many of them have very broad mass ratio priors. We have mass ratio on the Y here. Many of them have very broad priors that aren't very constraining. Some of them do have posteriors that are very inconsistent with equal mass ratio. So this is interesting, right? This is telling us maybe a little bit about the formation channel, right? If you had a formation channel that predicted only equal mass ratio binaries, you can rule that out for these systems. We also have some that have an effective spin greater than 0. The effective spin is a combination of the spins of the black holes relative to their own orbit. So an effective spin of 1 means both black holes are spinning rapidly and aligned with their orbit. A negative 1 is both rapidly misaligned with the orbit. So the orbit's going this way and the spins are facing the other direction. A 0 spin doesn't mean the black holes are not spinning. It can mean that. It can also mean that they're in plane. But we use this also to tell us about the formation channels. And you can see a lot of them are consistent with 0, again with some fairly broad posteriors. But you do have a couple here that are consistently greater than 0, right? This might be telling us that this is preferentially a formation channel that gives you aligned spins in your black holes, aligned spins with the orbit. If you had dynamical formation channels, you would expect to have a distribution that is centered on 0, but maybe a bit broader. So one thing that they do look for is any systems that are consistently negative, which would be a pretty good sign that you had a dynamical formation, where the two black holes were not together when they were born, and then they found each other and their spins are isotropic. Because we don't see that, this is maybe some argument against there being a formidable amount of dynamical formation in these progenitors. But that's a separate question that we're not going to talk about too much here. What we're really interested in is the chirp mass, which is the best measured mass property of the system. So I showed before the chirp is where it spikes toward the right where the two systems are merging. At the lowest masses, the chirp mass is really well measured. So this here on the X is the chirp mass in the detector frame. You can see here the width of the posterior is very, very narrow, right? So we measure the chirp mass. It's one of the best measured quantities of the whole system. The chirp mass is related to the component masses with this equation at the top. So this funny product and sum and the couple of powers. But it's a really easy thing to calculate if you know the masses of the components. It's much harder to find the masses of the components if you just have the chirp mass. If you have an estimate, if you have a really precise chirp mass and a sort of a broad posterior on your mass ratio, you're going to get a broad posterior on your individual component masses. So a lot of people do their inference on the component masses, but we find that it's actually much easier to work in chirp mass space. You can see here, this is chirp mass versus redshift. So for the lowest chirp mass systems, we only see up to a redshift of about 0.5. As you go to higher chirp mass, these are louder signals, so you can hear them from further away. So you're more sensitive to further away redshift for these higher mass, higher chirp mass systems. Here in the dashed lines, I show the relation between the source frame chirp mass and the detector frame chirp mass, because if a system merges very, very far away, that signal gets stretched on its way to us. It gets redshifted. And so the chirp mass that you detect at the LIGO detectors is going to be very slightly higher than the, well, maybe very slightly, maybe significantly higher than the one that is the actual source frame chirp mass. Because there's also some uncertainty in the redshift, there's a little bit of spread in the source frame chirp mass relative to the detector frame one. It's still a very well-measured property compared to some of the other ones. But the particular importance here is that the chirp mass is very, very precise at low masses. Compare that to the primary mass. So here is the distribution of the source frame chirp mass. So this is after including the redshift effect. The spread you get on the source frame chirp mass is much higher than the spread you get for, say, the primary mass. And people love to look at the primary mass and talk about features in the primary mass distribution. There's bumps, there's gaps, there's all sorts of interesting physics going on there. We argue that we can do a lot of the same inference really much better with the chirp mass for this reason. When we're comparing the models, it's difficult to measure the component masses from the data. We find it much easier to make a prediction of the chirp masses from our models, because our models tell us exactly what masses we're predicting for the two black holes, and it's so easy to calculate the chirp mass that it's a safer space to work in. When we look at the source frame chirp masses, particularly when we zoom in on this region between 5 and 30 solar masses, so the lower mass end where these detected chirp masses are really quite precisely defined, we start to see this nice three-peak structure, roughly at around 8-ish solar masses, another one around 13, and another sort of broader one around 27. Now, it's still early days, right? The data is not really, really conclusive. It may be the case that there's the two outer ones, and maybe sort of you could maybe hide that middle bump. Maybe it's a little more suppressed than this. But we're starting to see this kind of three-peak character to the chirp masses that is compelling, right? If there's structure in the chirp mass distribution that's telling us about the formation channel of these binaries, why would it be there? To understand the origin of these peaks, we turn to recent advances in stellar and core collapse theory. Now, from core collapse, 3D hydrodynamic core collapse simulations, which are incredibly complex and really push the boundaries of what we can do with the physics. Here is one particular study from Sukbold in 2016, looking at the outcomes of different supernovae under different models for the explosion. So the different rows are different models for the explosion, different assumptions on the physics that goes in as a function of your ZAMS mass of your progenitor. The outcomes are colored by green if it's got an explosion that gives you a neutron star at the end, black if it's a complete implosion, so there's no explosion but all the stellar material implodes onto itself into a black hole, and blue if you have an explosion and you form a neutron star but it doesn't all explode away, some of the material falls back onto the black hole and you have a fallback black hole, which may be lower mass. Maybe it would have had, a big natal kick, like we normally assume with neutron stars, but maybe that natal kick is scaled back a little bit. But it's maybe a black hole of a different character, a slightly lower mass. But as you can see, across these different assumptions on the physics, first off, there's a lot of stochasticity, right? There's a lot of areas where if you change your initial mass just a little bit, you get a completely different outcome, right? These are just randomness that we can't necessarily get around. But you do see areas that are quite robust, like this black region here, which is telling us that you form black holes, direct collapse black holes, consistently between roughly 22 and 24 solar masses. And then above that, you form neutron stars in an explosion, again, consistently. So we call these islands of explodability or non-explodability, where if you're exploding, you get the neutron star, and if you're not exploding, you get the black holes. But this feature seems to be robust, which is maybe a bit surprising. And we see this also in the detailed simulations from Bernard Muller's group, where here, again, you have the ZAMS mass, and the outcome is the colors of the points. The y-axis is showing this compactness parameter, which is defined here below. It's the amount of the radius that contains a certain amount of mass. So in this case, you see the psi 2.5 is telling you what is the radius that contains 2.5 solar masses of mass. And you can see the outcomes here as a function of your ZAMS mass. you get, again, this sort of peak of the black ones, which are the black holes, and then the red ones, which are the neutron stars. And you get this peak where you're forming black holes, and then above that, neutron stars again. So in particular, the distribution is non-monotonic. You don't have it where you form neutron stars up to a certain mass, and then black holes above that. That's no longer the running, accepted, the way the situation goes. When we look at the stellar models that go into these supernova models, we think that we can identify the origin of these islands from features in the progenitors themselves, in the structure of the core prior to core collapse. In these single-star models, we see similar bimodal peaks as a function of either your, again, your compactness parameter, or your central entropy, or your iron core mass. All three of these are ways of describing the core of the star prior to explosion, and all three of them show this peaky structure where that peak is roughly aligned with where we were forming black holes in the previous slide. Right? So we might argue that if you have a high compactness, or a high central entropy, or a high iron core mass, you have a harder time exploding the envelope, and you're more likely to form a black hole. Now, whether you explode or not is maybe not so important. Really, the key thing is if you have a high compactness, we think you should be forming a massive black hole, maybe from most of the stellar material. Maybe not all of it, maybe up through the helium layers, maybe not the hydrogen layers. But the idea being that if you have a higher value in any of these parameters, you're more likely to form a black hole. And if you don't, you're more likely to form a neutron star or a low-mass black hole. Some of this may be related to the explodability, as I said, but this is very, very uncertain. A lot of these detailed supernova models only run for 1 or 2 seconds in real time. I mean, not in computing time, but in terms of the simulation itself, these things are so complicated, you can only really get those first moments of the shock building up around the protoneutron star, and it can be a bit unclear if the model would eventually explode. They can't simulate for long enough to say for sure, but you can start to get a sense for the accretion onto the protoneutron star. If it's a higher accretion rate, maybe you're, again, more likely to form a black hole. A lot of the origin of these peaks come from neutrino-dominated burning, and I'm going to say thank you to Eva. She actually gave me these exact slides, so I'm going to try and explain Eva's research in front of her, so I hope this goes well. But this is really coming from, so if we take the peak here, so these 1, 2, and 3 correspond to, in mass space, regions on either side of this compactness peak. So 2 is in the middle of the peak, where you're forming black holes, and 1 and 3 are on either side of these peaks, where you're forming neutron stars. Now, in the one case, so on the left, you have some radiative, this is in carbon burning, you have some radiative burning due to neutrino losses, which means that your core here, your burning front of your carbon-burning core, is contracting a little bit, which heats things up, which means you push out a convective region, and as the core contracts, this burning front moves out en masse and grows a fuel-free core. When you get to silicon burning, you have a large amount of fuel, so you grow a low-mass iron core. It doesn't go out that far. And so you end up with, in this case, a lower-mass iron core, which we said is correlated to neutron star formation. If you have a slightly higher mass core, so now you're dealing with the system in the peak, you have higher neutrino losses, a slightly lower amount of fuel. Again, this is for carbon burning. Because you have higher neutrino losses, your core is contracting more, so you're able to push out that burning front further. This is this convective burning front here, which means you can burn more of your fuel. So you're more efficiently burning through all the fuel in your core, and you can construct a larger iron core by the time you get to silicon burning. Right? And so here you can see the difference. You have this smaller core. This is not going to be big enough to directly collapse. This bigger iron core will be. If you continue this process of increasing your mass and increasing the neutrino emissions, you'll have an even greater amount of contraction, but at some point, your burning front passes the effective Chandrasekhar mass, and this means that you're going to ignite in your core earlier than you would have before. So before you've had a chance to burn through all this fuel, you ignite in your core, and you start the next round of burning, and you end up forming, again, a lower mass iron core. So these features that we see in the compactness and in the central entropy and in the iron core mass are coming from this neutrino-dominated burning, which is itself non-monotonic, right? As you dial up the core mass, as you dial up the amount of neutrino emissions, eventually, because you pass this effective Chandrasekhar mass, you come back down and you don't have explosions the way you do in the peak. Sorry, this is the one that doesn't have explosions. This is the one that returns to be an exploding model. Of course, most massive stars that are going to form black holes or neutron stars are coming from binaries. I think this is well known in this room. And so we want to know the impact of binarity on the situation, right? We're looking at the structure of these cores. what effect does it have on the structure if you strip off envelope material before the supernova. Any short timescale mass loss can strip off the stellar envelope. This can be from binary mass transfer, right, if you have a Roche-Loeb overflow event or a common envelope, or strong stellar winds, if you have, for example, LBV winds that radiate a lot of the envelope even in a single star, but they do it very, very quickly. If this occurs before your helium shell burning, it will modify the core structure compared to an unstripped core of equal mass. So here is a plot using tulips, which is IvS code, which looks at two stars. One's a single star, one's a binary strip star, with the same core helium mass. And you can see the differences in the structure that you get, even though it's the same core mass, just from the fact that you've had binary stripping. So the statement is that when you have a binary strip star, or a strong-winded strip star, you're going to change the core structure, and this should have an impact on the explodability or non-explodability, or the black hole forming likelihood of a given progenitor. So you can't just look at the helium core mass, because the mass transfer history will be relevant. This is a plot from Fabian Schneider's recent work, looking at a similar thing. This is at core helium exhaustion, the carbon-oxygen core mass, and the core carbon fraction for single stars and those that have experienced mass transfer at different phases during their evolution. So the different phases are case A, case B, and case C. Case A refers to main sequence mass loss. Case B refers to Hertzsprung gap mass loss, so after it's left the main sequence. And case C is post-helium burning. And what you see is that you get these two sort of trends here, where this lower branch comes from single stars or case C stars. So if you've already passed core helium burning, you've sort of set the structure. It doesn't matter if you then lose your envelope. You're going to have the same sort of core carbon mass fraction as you do for a single star. But if you strip earlier than that, either case A or case B, you end up on this upper branch where you have a slightly higher core carbon mass fraction as a function of your carbon-oxygen core mass. And this mass fraction, this core carbon mass fraction, is the fuel we saw before. So if you have a higher amount of fuel, it changes whether you're going to be in that peak or not. This also has an effect on the morphology and timescale of the explosion itself. So here's some work from David Vartanian from a few years ago, looking at, again, binary versus single stars with the same initial mass. This is a 14 solar mass initial star. And I don't want to get too much into the details of this one, but you can see the dashed lines are your single star, your solid lines are your binary star, and looking at a variety of different attributes of this model, either the density of the model as a function of mass, or the composition, or the explosion radius and accretion rate. You can see there's very qualitatively large differences whether you have the single star or the binary strip star. And in particular, you can see in the morphology, these things look really, really different. So all of this to say, binarity really matters, right? Historically, we've just used the core mass, either the helium core mass or the carbon-oxygen core mass, to decide what is the outcome of this explosion. And this work has really shown that you need to look not just at the core mass, but really at the mass transfer history. What is this doing to the structure, and what does that tell us about which stars are forming black holes and not? Building on this, Fabian and Eva and a few others did a sort of a similar study looking at the effect of the stripping on your core compactness. So this is for solar metallicity on the top and solar by 10 on the bottom. What is the compactness parameter, this chi 2.5, as a function of your CO core mass all the way through this for these detailed single star models, detailed stellar evolution models, which are either single or binary stripped. And you can see, as you account for stripping, the blue lines here are the stripping ones, you push that compactness peak a little bit to the left. So you have a slightly different carbon-oxygen core mass at which you will get black hole formation from a strip star compared to a single star. You also have a metallicity effect here that you can see on the bottom. Those peaks are slightly shifted. It's not so dramatic in terms of the metallicity, but you do see a difference there. So this will matter, especially because a lot of the binary black holes that we see with LIGO are coming from lower metallicity systems. And so, precisely if this stripping occurs before helium shell burning, helium core burning, it will modify the core structure compared to an unstripped star with a core of an equal mass. And this affects the positions of those peaks. Now, what this is telling us is that if we think that black holes are forming in direct collapse from these peaks, from either this compactness peak or higher up, when you form a direct collapse black hole and you assume most of the mass of that star, or at least up to the helium layers of the mass of that star, will end up in this black hole, that gives you a bimodality in your black hole masses. So this is looking at, from the same study, this is looking at the masses of those black holes that you get from either the low compactness peak here on the left or the upper compactness peak here on the right. We also, I mentioned before, you have some fallback black holes. These are coming from things off of those peaks that maybe were neutron stars, but if they accreted a little bit during the fallback process, maybe they turned into black holes. And we don't know much about the fallback process, but for simplifying assumptions, probably it's not going to give you a particularly massive black hole. So they sort of end up even lower mass than the low compactness peak black holes. But something around 7 to 8 solar masses we might expect is where this lower mass peak is coming from. Again, this is assuming that high compactness is indicative of a core that is harder to explode. It's got a higher binding energy, so it's more likely to collapse. If we believe this, and some of the supernova models are sort of leaning in this direction, then we should get a direct collapse black hole that has no mass loss, no natal kick, and no observed supernova. So we now look for red supergiants that suddenly disappear as evidence of these black hole forming implosions. They don't produce a luminous transient for us to see. The no mass loss and no natal kick are approximations. Maybe they have a little bit of mass loss and a little bit of natal kick. Probably not a whole lot. But this bimodality in compactness really leads us to a bimodality in the black hole masses. And this is really the takeaway from this stellar evolution work, is that we have a reason to believe that black hole masses are bimodal intrinsically following stellar evolution. I maybe should have mentioned before, these are only stellar mass black holes. We're not looking at supermassive or intermediate mass black holes, just the ones that you get from stars. Building on this, if we want to form binary black holes, you're drawing pairs of black holes from this bimodal distribution. So if you do this randomly, then you should get sometimes a pair of 2 low-mass black holes, sometimes a pair of 2 high-mass black holes, and sometimes a mixture of the two. And that was maybe the sort of the last prediction of this paper, is that you should get a 3-peak feature in your chirp mass distribution from the combinations of the pairing of these bimodal black holes. So because your black holes are bimodal, your chirp masses should be trimodal. You could also look at the sum of the masses, that should also be trimodal, but anything that accounts for both should have this 3-peak structure to them. But what this study can't tell you is which of these peaks dominate. They argued that this middle one, this mixture of high and low mass black holes, should be subdominant. So maybe we only see 2 peaks. There should be a third one in there, but maybe it'll take a long time before we really see it. But the idea is that from the stellar evolution, we should predict 3 peaks. But binary black holes are a very rare outcome of a stellar and binary evolution. So if you want to run a big MESA grid to do this, nowadays you can do a whole population study with MESA and produce some binary black holes, but it will take a lot of computing time, and you can't then vary the assumptions of your physics that goes in. It's too complicated to do a parameter study where you're looking at many different parameter variations. You can just do sort of one assumption and see what sort of black holes you get if you're doing your detailed stellar evolution modeling. So to predict the relative heights of these chirp mass peaks and how robust they are, we turn to rapid population synthesis, which I think, as most of you know, is really my expertise. So for this, we use the Rapid Binary PopSynth Code COMPASS, which stands for Compact Object Mergers, Populations, Astrophysics, and Statistics. This is what I spent my PhD working on. COMPASS is built on analytical fits to single-star evolution tracks. So it wasn't with MESA, but effectively you think of running MESA on a variety of different single stars. You fix your physics. You figure out what the track looks like in the HR diagram, and you fit a polynomial to these tracks to say, okay, here's how the luminosity and the radius and things change as a function of time and core mass and all that. And then you apply on top of that parameterized approximations to detailed binary physics. So things like stable mass transfer, common envelope, stellar winds, all of these things that are intrinsically complex, and we have a lot of experts in the room on doing these things in more than just 1D, can tell you that these things are really, really non-trivial to do. But we can take the results of these studies and try and fit simplified approximations to them to feed into the rapid PopSynth code so that you can get things that run fast. So we dial down the detail so we can dial up the speed. And what we get is that with COMPASS, you can evolve a single binary in about 0.1 seconds, or CPU seconds if you're parallelizing and all that, which means you can do 1 million binaries in just a few hours on a cluster. So I do this all the time. It's a very easy thing to do. You choose your physics model. You choose your assumptions on what winds you're going to do, what your accretion rate's going to be, what supernova model you're going to run with. A few hours later, you have a population of binary black holes that you can study, and then you tweak those, and you get a new population, and you can compare the effect of that physics that was very uncertain, that you've parameterized very coarsely on the outcome populations that you have. Of course, the code is open source, so if you're curious or you want to get involved, please reach out. Here are the papers that went into the development of this code. And this here on the right is a schematic of what a typical binary evolution might look like. This is one particular formation channel for, in this case, a double neutron star merger from Torres et al. 2017. This just highlights some of the phases of the life of a binary that we might be interested in. So we're not only doing binary black holes or binary neutron stars. There's a lot of other things that we can predict. But when you're using the rapid pop synth, because it goes so fast, it gives you access to these rare outcomes that might be harder to do with detailed models. So for example, you have a few different mass transfer cases, mass transfer events up there. You have a high mass X-ray binary, you have a couple of supernovae, you have different kinds of binaries that you might observe, right? So at any point in this evolution, you might say, well, let's make a prediction for what our high mass X-ray binaries look like. And then you can compare that to the observed ones. And if you account for your selection effects properly, you can get maybe a constraint on that phase. And that can build up maybe your knowledge for later phases, right? If you have a better constraint on your natal kicks from maybe isolated pulsars or high mass X-ray binaries or what have you, then you can get a better prediction for your formation of double neutron stars or binary black holes or things like that. But in this case, we focused just on the formation of the binary black holes. In order to do this, you need to sample over a variety of initial conditions. So these are things that are chosen at the beginning based on whatever the industry standard is. There are different ways to do this, but we choose uncorrelated initial conditions that follow the Krupa IMF for the primary mass, a uniform mass ratio, flattened log separation distribution, zero eccentricity, which is not such a bad assumption for this kind of study, and a flat in log metallicity, which is key. I'll come back to this. So this is not, I would say, physically motivated. It's a thing that we do just to get some output from the pop synth, but it's not the final choice for the metallicity distribution that we get. And you can see here, this is sort of what it looks like, at least for the first type of interaction that the binary might have. This is a plot I made a few years ago for a different study. And you can see that it's sort of uniformly sampled in the periapsis, or the separation, the log separation, and the mass ratio. And the colors and size and shape tell you about what the star was, or what the binary conditions were at the first interaction. So it's not maybe so important to focus on this, but this is sort of what we're looking at when we feed in these simulations. You're running 1 million different binaries, sampled over initial conditions, as physically motivated as you can be to try and see what the outcomes are. For this study, we've invoked this new bimodal core collapse model. So we had the detailed evolution models from Eva and Fabian and their team. And then with a PhD student at HITS, they came up with this model for what the outcomes of an explosion would be as a function of your carbon-oxygen core mass and your metallicity, and now newly also your mass transfer history. So this is the key difference, right? You think interacting binaries should make a difference. So you have a different outcome space, slightly different, if you've had no mass transfer versus case A, case B, or case C. So again, this is just a different stage of your star when it first interacted. This will tell you a slightly different outcome landscape. And the outcome landscape really looks like this. So on the left, if you are at the lowest carbon-oxygen core masses, you have neutron star formation, an explosion, a natal kick, all these sorts of things. On the right, in black, you have black hole formation. Also, in this strip here, you have black hole formation. These are your direct collapse black holes, no mass loss, no natal kick, takes the mass of the helium core of the progenitor. And this is coming from that low compactness peak. In red is this neutron star or black hole region. This is a region of stochasticity where we don't really know so much what's going on. The supernova simulations don't really resolve a very precise answer. And so we take as a default in these models that with 90% probability, you're going to get a neutron star, 10% probability, a fallback black hole, and then you choose your fallback fraction. We take 0.5 as a default. These are all things that we can vary, but we just want to have a choice for something. And you can see there's a metallicity dependence here. So as we move outside of the range where the simulations were run, which was solar and solar by 10, we are not so sure what these models should be doing. We didn't run detailed models at lower metallicity, which is unfortunate because this is where a lot of the binary black holes will form. And so in order to investigate the importance of our lack of knowledge outside this region of interpolation, we've chosen a few different extrapolation models. So it's not so important what these are just different ways to extend those lines out. So some of them are continuing the line linearly, some are a direct drop-off, a nearest neighbor extrapolation, and then another sort of intermediate one, which is an extension and a drop-off. These end up not mattering so much, but it's important to mention that we've explored uncertainties in this low metallicity regime. So when we run the population synthesis, we can take from this the masses of the black holes and the binary black holes, the chirp masses of the binary black holes that we simulate. So in the first two plots, these are the masses of individual black holes. The right plot are the chirp masses. The left one are all the black holes that we form. So unsurprisingly, we get a bimodal distribution. This is just seeing that we get out what we put into it. No surprises there. In the middle, these are only the black holes, the individual black holes that will end up in binary black holes. So these are the components of the merging binary black holes that LIGO will see. You still see a bimodality. There's some new character to it. In red are the direct collapse black holes. In yellow are the fallback ones. And then in blue, purplish, we have these chemically homogeneous binaries. These are things that Pablo made his name studying. These are systems that equalize in mass and are so close and so well mixed that they avoid expansion after the main sequence. They're kind of pure helium. There's a lot of uncertainties in these stars, and they only affect higher masses. So for this study, we ignore these. They probably do make a difference in the overall chirp masses that LIGO is seeing at the higher masses. For our case, we put them here, and then we don't talk about them again. And you can see here on the right, they only really affect the highest mass things anyway. So as long as we focus on the lower masses, this isn't such a bad simplification. And it allows us to focus on the physics that we're more interested in. But here on the right, as I said, you have your chirp masses coming from the population synthesis. You see your nice 3 peaks as predicted. That middle one is a little stronger than maybe previously anticipated. But crucially here, we've sampled again from a log uniform in metallicity distribution. So this is not what we expect to see in LIGO. This is just the direct outcome, the output of the population synthesis. Building on this, when we look at the formation channels of the binary black holes, we can categorize them in terms of whether the binaries experienced only stable mass transfer in their whole lives, or if they experienced a common envelope event. There are many other ways, more kind of fine-tuned ways, to distinguish the evolutionary formation channels of binary black holes, but this is sort of a nice first-order corsifying way to distinguish 2 different classes of formation channels. So you can see the stable mass transfer ones are the hollow lines, common envelope are the solid filled-in ones, and colors correspond to metallicity. Now, as I said before, your lowest metallicity systems form binary black holes more efficiently. So you see a lot of dark colors here. That's not surprising. Again, this is something that's known, and it's nice to see it reproduced here. You can see that the dark ones here tend to skew towards lower, this is the orbital period of the binary black hole at formation. Unsurprisingly, there's more of the dark ones at the bottom because common envelopes lead to rapid inspiraling. So you have more tight binaries at the formation of the binary black hole from common envelope than you do from stable mass transfer. Again, not surprising. Nice to see it reproduced here. The surprising thing is the way that these formation channels are distinguished in the peaks that we see in the 3 peaks coming from the chirp mass distribution, these 3 peaks that we formed from the mixtures of either 2 low mass or 2 high mass or a low mass, high mass black hole. You can see at the highest chirp masses around the peak around 20, we're almost exclusively coming from stable mass transfer channel. This middle peak, the low mass plus high mass, is coming from almost exclusively common envelope. And this lowest mass peak, the low mass binaries, are coming from a mix of both, but mostly common envelope. And this is very telling for what we can do with this physics, because there's a lot of uncertainties that go into your binary formation modeling. We know this. We don't attempt to say that we have the right formation model or the right choice of physics, but we want to explore the uncertainties in this physics. And one thing that we can do is we can change the importance of your stable or unstable channels. You can dial up your mass transfer accretion efficiency in stable mass transfer, or your angular momentum losses, or you can change your common envelope alpha. For those that aren't familiar, these are just the sort of the common parameters that we might think, oh, we don't really know what we're doing with this one. Let's change it and see what happens. And you can see, because you're getting a different, each of these different peaks has a different weighting from each of these channels. If you change your physics, you should be able to change the relative heights of these peaks. So that's sort of the assumption that we start with. We're going to show that that's well motivated later. But because we were using this log uniform and metallicity distribution for the sampling, which is unphysical, in order to make a prediction that we can compare to the LIGO results, we need to convolve this with an adopted model for the cosmic metallicity-specific star formation history, which is this SZZ or ZZ, wherever you're from, where we have the overall star formation rate is this black line, this normalization as a function of redshift. This is what is the number of stars being produced per cubic megaparsec per year, in terms of solar masses. And then color is your metallicity. So at the early universe, you have the lowest metallicity things. As you come to later in the universe, obviously you get higher metallicity star-forming material. No surprises there. This is a very simple model from Lieke van Son from a few years ago, who did it again for COMPAS, so it's right there. It's very easy to work with. It's not necessarily the most physically motivated model, but it's one that we can start with. It's a good starter model. And what we do is we can reweigh our population. Because we sampled log uniformly originally, we can just reweigh all these outputs according to how likely it is to form a star of that metallicity at that redshift. And then you know from your pop synth, okay, well, this thing took this long to form a binary black hole, and then it formed at this period, and so it took this long to merge. And then you do all your reweighing, you figure out when a system of a given chirp mass merged in the universe, and that tells you if you can see it in LIGO today. So if you have a very, very short period, low mass system that merged very early in the universe, probably by now its signal is very dim and you're going to miss it. Right? With future detectors, maybe you'll see it, but that's the idea. We also apply detector biases, which include the sensitivity to masses over the whole LIGO observing period. We assume, for simplicity, a sensitivity equivalent to the observing run 3 or O3 sensitivity across a 1-year baseline. This is a very approximate detector bias method. I can talk more about how we would improve on that later, but in effect, over time, LIGO is improving, and so the sensitivity grows, and this is a difficult thing to model. So we start with this kind of simplistic toy model just to get a sense of what we're going to see. And when we do this convolution, so this is, again, the expected source frame chirp mass distribution after convolution with the cosmic star formation history. And what you see is that before, you had a little more support for these 2 lower peaks. Now they've gone down. And this is largely a function of that detector bias. You're less sensitive to the lower chirp mass things. So if you had an otherwise equal formation of these systems, you would expect those to come down a little bit. Again, you can still see that the highest peak, the high mass plus high mass, is still completely formed by stable mass transfer. Again, these are the hollow colors are stable and the solid colors are common envelope. Now the coloring is according to redshift. So the darkest colors are the ones that are merging really, really nearby in the universe. And you only get the lowest redshift systems contributing to these lowest 2 peaks. At slightly higher redshifts, up to 0.5, you get things closer to that 20 solar mass in chirp mass merging that you can measure with current LIGO observatories. But you still see the 3 peaks. The lower 2 are suppressed, but you still should see them. And the overall rate is actually not so bad. So we get, if you add these 2 up, you get something like 60 mergers per year. Compare that with roughly 52 from the LVK in this mass range of 5 to 30 solar masses, where the median, we're 52 with a median in that range. So it's maybe not exactly 52, but kind of close to it. And when you're looking at binary black hole merger rate comparisons, this is pretty good. Usually we're off by several orders of magnitude. So here we're not saying that this is the right model, but we're definitely moving in the right direction. So with this framework in place, we can now explore the variations to the assumed physics that went in. So that was just a default model that we worked with. But we can vary the physics that we've assumed, rerun our population synthesis, and compare those new outputs directly with the LVK data. So this is a very ugly plot, and I advise master's students in the room to not show a plot like this in their presentations. There's a lot going on here. I'm not going to go into detail about what all these things are saying, but in short, what you have at the top are the traditional black hole formation models, and everything else is the bimodal black hole, this new bimodal black hole formation model with some other variation to the physics. And what you're looking at is the observed rate of mergers that you would expect as a function of your source frame chirp mass from this 1-year assumed observing time. And what we see is that in all of the bimodal black hole formation models, we always see 3 peaks. Sometimes that third one is really, really suppressed. It might be off the plot, but it's always 3. And what in particular you find is that this gap around 10 solar masses, which we do see quite prominently in the data, is really well reproduced in these bimodal black hole models. We also see that as we vary the physics, and some of the physics variations here are for things like I said before, so we vary our fallback fraction and the natal kicks, we vary the accretion efficiency and the angular momentum during different kinds of mass transfer. So if you have mass transfer onto a star versus onto a black hole, you might have different kinds of angular momentum loss that we can parameterize, even if we don't understand the physics completely, why it would be that way. As we vary these things, you see, as predicted, the relative heights of these peaks are changing. So if you argue, here in the second row are the default models, we can see that that red bump, that third red bump is quite high. This doesn't mean that we are definitely overproducing with our model. What it means is that we need to find a variation that dials that down a little bit. Within the uncertainties of binary evolution physics, we can tune those heights of those peaks to get a better match to the data. But it's within the realm of our uncertainties that we can do this. Whereas that dip at 10 solar masses is really quite robust, is really quite present in all these models, except for the traditional supernova formation ones. So if we're really looking just at that 10 solar mass gap, all of the bimodal black hole ones can reproduce it, and none of the traditional black hole formation models can. So these are the ones that aren't bimodal in nature, and because they're not bimodal, they're continuous, and they fill that 10 solar mass gap in chirp mass more easily. You can see in the traditional ones, you don't really see any 3-peak structure at all. So if you believe in the 3-peak structure, it's really telling you that you should be at least looking more into this bimodal black hole formation model. Now, I mentioned that this cosmic star formation model that we used from Lieke van Son's work is not the most physically motivated. There's some issues with it that we're starting to identify, and the overall star formation rate might be quite high. But again, like with all things in PopSynth, we can vary it. So it's itself parameterized, and we can choose different choices for how we parameterize this star formation history and the metallicity distribution within it. And when we use these variations that Lieke has provided, we get all of these different curves. So for any given plot, all the lines in it are just a different choice of that cosmic star formation history model. The top 3 are, again, your traditional supernova models, 3 of the traditional ones. And the bottom 2 are bimodal ones. So this is our default one in the 4th line. And then the bottom line is one with slightly enhanced angular momentum loss into a black hole, which we argue is maybe one of the better fitting ones of this model. Still some issues, but at least it's doing quite well in this high peak. And what we find is that as we change the cosmic star formation history variations, you get an overall rescaling in the absolute number of systems that you expect. No surprises there. If you have a higher star formation rate, you expect more binary black holes. That's fine. You get a change in the overall scaling, and you get some sharpening or softening of some of the features, but you don't ever produce new features. You don't produce a peak or destroy a peak or a gap where there wasn't one before. And so what we argue is that even though we're uncertain in our cosmic star formation variations, you can't explain this 10 solar mass gap with these uncertainties. We also find that this middle peak, which was originally predicted to be more absent, that we didn't think that we'd be able to see it in the LIGO things, in the LIGO data, is more prominent than expected. And this is actually quite intriguing. We think that this is coming from a previously unrecognized formation channel for binary black holes that hasn't really been talked about in the literature as far as we could find. It's been talked about in the context of, I believe it was X-ray binaries, I'm forgetting exactly what it was, from Van Beveren, but not in the context of binary black holes. This is what we're calling the LBV channel, where you have a very unequal mass ratio binary at the start, and the more massive system hits the Humphrey-Davis limit and ignites strong LBV winds. And these strong LBV winds rapidly strip the primary before it has a chance to expand. So it keeps well, it doesn't keep its size, but it doesn't expand significantly, and you avoid mass transfer before the formation of the first black hole. This is not something that is discussed in binary black hole modeling communities. Usually you think that there's always a first stage of mass transfer and probably a second one before each of the black holes form. So in this really kind of unusual channel, you don't have mass transfer before that first black hole forms. Because the secondary is lower mass, it doesn't hit the Humphrey-Davis limit, it doesn't experience LBV wind mass loss, it expands as normal, and you do have a mass transfer phase, typically a common envelope, from on top of this primary black hole that you formed. Which means that you then spiral in, and you're able to form a very unequal mass ratio binary black hole with no mass ratio reversal. So a lot of communities talk about mass ratio reversal as this kind of nice, it's maybe thought to be one of the primary features of isolated binary evolution, which is what we're looking at here. But in this formation channel, you don't see mass ratio reversal, even though they're very unequal in mass. And it's because it's a low mass and a high mass, so you naturally get that inequality. But we're very excited about this. Obviously, we want to do a little more research into it, but it seems to be quite robust, at least in these simulations. So in conclusion, the latest LDK observations show a trimodality in chirp mass. The bimodal black hole model naturally produces a trimodality where the traditional models cannot. We think that we've found this cool new LBV formation channel for binary black holes that's been underrepresented or under-discussed in the literature. And if we think that this bimodal black hole formation is giving rise to these peaks, this gives us non-degenerate constraints on our binary evolution physics from the relative heights of these peaks. So if you think that your black hole angular momentum loss should be higher, then that third peak comes down a little bit. There's different reasons for this, but that's a unique constraint you get from on binary evolution. You can also get constraints on your internal stellar physics because the nuclear reaction rates that are uncertain that go into your stellar evolution, as well as the winds, change the positions of those peaks. So some of the peaks that we saw, especially at the lowest masses, are maybe a little bit skewed to the right? Maybe we think that they should actually be a little bit further to the left. This is within the realm of the uncertainties from our stellar evolution physics, our single star models. So we can maybe tune our nuclear reaction rates or our winds to the positions of these peaks. And then the overall normalization is really only dependent, the cosmic star formation history seems to have the strongest effect on the overall normalization. So if we think that we're getting the shape of the distribution right, but the normalization wrong, maybe that's coming from the cosmic star formation history. So this is really nice because it disentangles some of these competing effects. And if we believe that this lowest mass peak in particular, this 10 solar mass gap and the drop down to it, is really there and really present only because of this bimodal black hole mass model. This is a universal structure feature which should be present if we can see out to the early universe with future gravitational wave detectors. If we're seeing all of the black hole mergers, particularly at the lowest masses, out to this early universe, out to high redshifts, then these universal structure features can be used as standard sirens to do precision cosmology and better measure things like H0. And so this is a paper that just came out in the last week or two. We finally got it in the archive. And as a shameless plug, maybe some of you all know this, but I'm applying for grants and fellowships this year. So if you know of anything, let me know. And I'm happy to take questions.
Thank you, Reinhold. Great talk. Okay. So I have a couple of questions because this will change how I present this on Tuesday. So the first thing is, how confident are you in that you're actually seeing a triple peak in the LIGO data? Because, I mean, the main claim that there is a gap on the tensor mass black holes that is clearly explained by this bimodality in the black hole distribution is very obvious in the data. But how consistent are all the observations with a triple peak?
This is what I'll show to answer your question. It's maybe not so strong the evidence for that third peak, that middle peak, but it does look like we have this very prominent lower peak that seems to be statistically robust. And this dip next to it, so the peak at 8 and the dip at 10 do seem to be very prominent. And then this rise again at 25 also seems to be quite present. If you want to argue that there's maybe a slow rise up from 10 to 25 and no middle peak, you can suppress that. It doesn't mean that the physics is wrong. It just means that we need to reweigh what we chose to dial it down a little bit. But there's maybe less strong evidence for that middle peak, but some I would say fairly strong, especially for the lowest one.
Okay, thanks. And the second question is a bit, unrelated, but it was regarding this LBV channel. How constrained is the LBV mass loss right now? Because I remember back in the days when I was working with Compass, it was creating really weird features from time to time.
It does do weird things. So fortunately, because it's undeniably a fast mass loss phase, the uncertainties in the LBV mass loss are not actually a big problem for the LBV formation model. So let's say you thought there was, say, an order or two of magnitude uncertainty in the rate of LBV wind mass loss. As long as it's shorter than the nuclear timescale, as long as it prevents the star from expanding across the Hertzsprung gap, which it needs to, it's going to be LBV mass loss. And as long as it's longer than the orbital timescale, which it would be hard to be shorter than that, then you're kind of safe. It should strip off the envelope, and you end up with a thing that doesn't expand with roughly the helium star mass. You could maybe get away with saying, well, okay, how much mass does it actually lose? Is it going to strip into the helium envelope a little bit? And that may change things a little bit. But you should still get one of these high mass direct collapse black holes from it.
Okay, perfect, thanks.
More questions?
Thank you, Reinhold. Great talk. I have a related question. So your LBV wind formation channel, what about changes in the orbital period due to wind accretion? I mean,
due to wind accretion?
Yeah, by secondary.
I wouldn't expect wind accretion to have a huge effect on these binaries. It might keep the binary from expanding a lot. You should still get the same formation channel. If you had wind accretion, you should be expanding less. So you would still have the system interacting when the companion overflows. You might get maybe more systems that interact that wouldn't otherwise, but I don't think it would be a huge difference.
The main thing I'm asking for, like, if you can lose like a lot of mass through LBV winds, right? And unless you really down your wind accretion efficiency, it will impact a lot your mass of second. I mean, at least that's what we see in the population synthesis model. Like, I have been doing that. Wind accretion is quite impactful and sometimes can be as good as even better than what you can get from mass transfer, stable mass transfer, I mean.
Are you talking about close binaries that are doing the wind accretion, and so a lot of it is focused? Because these are not necessarily very close binaries, right? You still have to expand without interacting at the tip of the main sequence.
But then how do you invoke common envelope?
That's in the second stage, right? Because there the companion is expanding, so that's hit the red giant branch. So they're maybe close enough for a red giant interaction, but close enough for case B, case C, but not for late case A. It's something we can look into more. Yeah, we should talk about this.
Hi, I have two questions. One about ABVs, surprise. I was wondering, how does the ABV mass loss impact your orbit, because I was thinking if you lose a lot of mass, then your orbit should widen, and I'm curious how you get then two close black holes that merge in Hubble time.
Yep, so you do get widening. This was my comment before, that as long as it's longer than the orbital timescale, it's not like a supernova will widen and induce eccentricity. With wind mass loss, as long as it's longer than the orbital timescale, you get just a widening that is well understood. For the amount of mass you lose, you kind of know how much you widen. And the reason you get a tight binary at the end is because the secondary expands, and then you get this common envelope that brings them together. It's just a single common envelope event.
Okay. And other question, in the super big plot that we don't encourage other people to show, I was wondering, so there you have a different spacing for the priors of the observations, and you can see there's another peak at 6 solar masses.
You caught me on that one. Okay, so this is something, so when I made the earlier plot that kind of more clearly shows these 3 peaks, this is a result of the KDE bandwidthing. So this is a more or less subjective choice. What we've done here is been a little more careful in that choice. So in the earlier one, I use an equal bandwidth for all of the binaries that we use from the observations. Here, you're talking about this peak here at around 6 solar masses. This is coming from very, very precisely measured systems. There's 2 in there that are about 6 solar masses in chirp mass. And because they're so precisely measured, if you choose a KDE bandwidth that's as narrow as those posteriors, you end up with a thing that is kind of seemingly like a lower mass peak. Because there's only 2, we're not confident that this is a statistically distinct peak to the higher one, even though it looks it here. And at the end of the day, it kind of doesn't matter if it's a distinct peak or not, because we still are not reproducing those masses. So in the bimodal black hole mass model, one of the drawbacks right now is that we're not able to reproduce those lowest masses, whether you count them as part of that peak or not. But yeah, that's a good eye. We're a little bit, I show the other one because it kind of looks nicer for the 3 peaks. Otherwise, I get this question more often.
Thank you.
Yeah.
Other questions?
Yeah, thanks for the nice talk. I have a very annoying question. What would happen if you include triples? How much is that expected to maybe spread out the distribution, or?
So it's a great question. So if you have triples, or if you have any other formation channel for binary black holes, your dynamics or or other sort of more exotic ones, as long as you're forming the black holes from stars, from stellar evolution, and the black holes are not accreting significantly, and as long as you don't have, for example, a single star that when it collapses, it keeps its hydrogen envelope, because in these cases you're always stripped, so you don't have any hydrogen left to collapse. As long as you're forming it from one of these channels, you should still see the bimodality in the black hole masses. You might change then the relative heights of these peaks, so maybe you can't get the constraints on binary evolution that we claim you can. For example, if you had dynamical formation contributing a lot at 20 solar masses, you had a lot of these kinds of black holes contributing there, that would throw off the height of that peak, which would be a problem. But because the prediction is coming from the stellar evolution, we think that the bimodal black hole mass spectrum is pretty robust. You can maybe pollute it in that gap a little bit if you have high fallback. A high fallback fraction does pollute that gap, which you can actually see here. We explored fallback in this 4th row. The yellow lines are the fallback ones, and if you have complete fallback onto your fallback black holes, that's that topmost line that actually is quite far up, and this is the assumption that you never have really a fallback black hole. Everything is direct collapse, which is maybe not also physically motivated, but it does fill those dips quite a bit. As far as what triples would do, yeah, again, as long as you have things forming from stars, you should still see the peaks there. The caveat to the black hole masses not being bimodal might come from, for example, like an AGN disk formation channel, where you can have maybe a lot of accretion, or one of these exotic stars that are sitting in stars, black holes sitting in stars that accrete super-Eddington for a long time. There are other ways to modify the mass of a black hole, but for most formation channels, you shouldn't have a huge change from what it was born with by the time of a merger.
And another quick question, more on the observational side. So we have, hopefully we are going to find more and more black holes around us in the galaxy, in the LMC, SMC. Would that build evidence towards this in some way? Do you expect?
Absolutely. Yeah, the ones that we see coming with Gaia and other surveys, if bimodality is really the truth in black hole formation, that should be apparent in the ones that we're expecting to see. That's a very strong prediction of this model. I don't know if anyone wants to respond to that or have a new question.
Very final response.
Yeah, I just wanted to say that I had actually a student in Heidelberg who worked exactly on this, looking at the masses of black holes from electromagnetic studies to see if we see the same features, because in our idea of how this like black hole formation occurs, it should really happen in all stars, so also in these ones. And so that would be a way to test this model. And so far we don't have enough observations, but hopefully with Gaia we should get 1,000 more black holes, and then we can test this.
Okay, we're at the hour, so we thank Reinhold again for talk.
Thank you.
And is there a seminar next week? Yes, Eva is giving a seminar next week, so we will continue a bit in this. No, ooh. Okay, so Eva will make everything explode.